Hello, Grade 12 GED students 2019-2020. We are continuing about Topic 2 Superposition of Waves, Lesson 2.5 as illustrated in your syllabus, Standing Waves in Closed Columns. Objectives are to show the formation of standing waves in closed columns, to derive the general expression for the frequency of the nth mode of vibration of standing waves in closed columns, to calculate the speed of sound in air using stationary waves. Now, how standing waves are formed? Now, first of all, what is a closed column? The pipe open at one end here and closed at other is known as closed tube. So this is closed end and this is an opened end. If waves with some frequency are sent through the closed tube, so here waves are sent, the waves get reflect. They will hit here the closed end and they will reflect back. So if the incident and the reflected waves have the same frequency, with the same frequency and opposite direction, so they will superpose each other, forming stationary or standing wave. So they are forming standing waves. Okay, so be careful here. We have incident and reflected waves with same frequency, same speed, same amplitude, and moving in opposite direction. That's why standing waves are formed. Now, it's very important here to know that nodes are formed at the closed end and antinodes are formed here at the open end. Why this is happening? Particles of air here, they are having the maximum displacement. They are moving forward and backward. But particles here stationary without any displacement. So all the particles here are stationary with no displacement, forming nodes, and particles at these positions are moving with maximum displacement, so they are antinodes. And it is very important to know here that here the particles are not moving up and down. Here the waves in the tube are longitudinal waves. Okay, for example, okay, now sound waves are sent through this tube, so they are air particles are moving forward and backward parallel to the direction of the propagation of the wave. So as we know that these waves, the wave that has been sent and the reflected wave, the incident and the reflected waves, they are longitudinal waves and carrying energy. The standing wave here, particles only moving backward and forward, and energy does not propagate. So, as we know, only for simplicity, we are representing this standing wave as transfer wave. Now, here now we are going to find an expression to calculate the frequency of the nth mode of vibration of standing waves in closed columns. If you have an empty glass, like of course air particles, it's filled with air particles, and if you are going to blow here over the top, open top, you will hear a sound like, yes. Why this is happening? Because air particles here, they have a resonance frequency. If we can make the particles move with or vibrate with their resonance frequency, so sounds or notes can be heard. So we want now to know the length of the air column that gives us these tones or notes or modes of vibration. Here we have open end tube, or close from this end and open from only one end, all with length L, the same tube. But we are using different frequencies or different tuning forks with different frequencies. So we want to calculate F1 and F2 and F3, how it is related to the wavelength. This is for getting different mode of vibrations. So for using different frequencies will give us different mode of vibrations for the same length here. So here we can hear sounds with different modes. So for the first mode of vibration, also it called the fundamental mode, there is only one node at the close end and antinode at the open end. For the second mode of vibration, we have two nodes and two antinodes. Of course, for all cases, the open end ends with antinode and there is a node at the close end. And this is the third mode of vibration. Here we have two nodes and two antinodes. Here we have three nodes and three antinodes. So to get L here, it is only lambda over 4. The adjacent, the separation between the node and antinode, it's only lambda over 4. So L equal to lambda over 4. Let's call this lambda 1 because we have here F1. Here we have our L equal to, this is lambda over 4. This is another lambda over 4. This is the third lambda over 4. So we have 3 lambda over 4. Let's call this lambda 2. Or change this, lambda 1, and this is lambda 2, and this is lambda 3. Okay. Now, coming here, this is giving us the third mode of vibration. We will count the nodes and antinodes, 1 node, 2, 3, and antinodes 1, 2, and also 3. So L here is, this is 1/4 of lambda, the second fourth, 3 lambda over 4, 4 lambda over 4, and 5 lambda over 4. So we have 5 lambda over 4. Okay, this can be lambda 3. Now I think looking at these formulas, we can get a general expression for lambda L, the length of air column, that gives us different modes of vibration. So L equal to 1 lambda over 4, 3 lambda over 4, 5 lambda over 4. So it is always an odd multiple of lambda over 4, lambda n, where n equal to 1, 2, 3, 4, and so on. What n represents? It represents the mode of vibration. If it's first, n equal to 1, second, n equal to 2, third, n equal to 3, and so on. It also represents the number of nodes or antinodes. Here we have only 1 node and 1 antinode. Here we have 2 nodes and 2 antinodes, 3 nodes and 3 antinodes. So from here we can get that our lambda n for any mode of vibration equal to 4L divided by 2n minus 1. Okay, we want now a formula for the frequency. From v equal to the speed of the wave here, okay, the speed of sound in the air, I mean, equal to f lambda. So we can write our f equal to v divided by lambda. So for n mode of vibration, fn, here we have lambda n, where v here is the speed of sound in air. Substituting the value of lambda from here, we can get that v over, this will be 4L, and we will get here 2n minus 1. This is the expression to calculate the frequency for any mode of vibration in the closed columns. Be careful here, our L is the same, lambda is changing, so we have different frequencies. Okay, now we can also change the length of the air column, okay, to calculate the speed of sound in air. By changing the length of air column, as in trombone, like for a trombone here, it's a wind musical instrument which has some holes here, yeah, and by changing, putting your finger here on different holes, we are changing the length of the air column. So that's why air will vibrate, and it will give different pattern or different notes or different mode of vibrations. Now, how to calculate? This is an experiment that can be used to calculate the speed of sound in air. The principle of reasoning in the closed tube at one end is used to calculate the speed of sound in air. A glass tube here is placed in a cylinder of water. So we are having here closed end and here open end. So by raising the tube, we are increasing the length of the air column. A vibrating tuning fork here, this is only one tuning fork, okay, with one tube. A vibrating tuning fork with a non-frequency is held above the open end of the glass tube. This will cause the air in to vibrate. The tube is gently raised, so increasing the length of the air column. At a certain position, a note becomes much louder. Very clear note we can hear. This is known as the first position of resonant, or the first mode of vibration, or the fundamental mode. So here we are hearing the first note. This means we came through a position where the frequency of the air particles are equal to the frequency of the tuning fork. Okay, so this L known as L1. So for the first position of resonance, let's us talk in terms of mode of vibration as in your book. Okay, the first position or first mode of vibration occurs when L1, this is L1, equal to, I think it's very clear that it's equal to lambda over 4. Yes, the separation between a node and the adjacent antinode. By raising the tube further, okay, the tube is raised further until a second resonance position is found here with this length. So we are in the second mode of vibration. So here we have our n equal to 1. Remember that. For the second mode of vibration, our L2 equal to, I think it's very clear that it is 3 lambda over 4. Here n equal to 2. Going back to our, here we have n equal to 2, so 2 times 2 is 4 minus 1 is 3. 3 lambda over 4 for the second mode of vibration. N equal to 2, so we are getting 3 lambda over 4. We can subtract L2 minus L1. So I think it's very clear that the difference between these two air columns is half a lambda. Yes? So this is the difference between two air columns, which is half a lambda. So L2 minus L1 will give us lambda over 2. Now, going back to the formula of the speed of air, sound in air, lambda f. Okay, now we have only one f here. Remember, we have only one f here. So our v equal to lambda f. From here, lambda equal to 2 times L2 minus L1. This is our lambda from here. So substituting here, we will get 2L2 minus L1 times lambda. This will give us the speed of sound in air. In this question, we are asked to calculate the frequency of the sound wave. What is the frequency of the sound wave when resonance is formed in the tube shown in the figure opposite? What this figure is showing, it's showing the length of the air column, which is giving us this mode of vibration. Now, let us know which mode of vibration this tube is forming. So, we have here the number of modes, 1, 2, 3, 4. So, it's the fourth mode of vibration. Also, we have antinodes 1, 2, 3, 4. So, our n equal to 4. Here, the speed of sound in the air is given as 340 meter per second. This is given. So we want to ask to calculate the frequency for the tuning fork here. What we have also, we have L, our L equal to 1.19 meters. Now, going back to the formula, that we have our Fn equal to V 2n minus 1 divided by 4L. So our V is 340, speed of sound in air, and our n equal to 4. We are in the fourth mode of vibration. So 2 times 4 minus 1. Then we have here 4 times L. Our L is 1.19. This will give us 500 hertz. This is the frequency. We have here an example. A tuning fork of 460 hertz. This is with 460 hertz. Cause resonance in the tube shown in the figure below when the length L of air column above the water is 18 point. So L1 is 18.3 centimeter, which is directly 0.183 meter. And another L, this is the L that we have. The second mode of vibration can be heard at a height of L2, which is equal to 55.8 centimeters. So it is 0.558 meter. Okay. Now calculate the speed of sound caused by the tuning fork in the air column. Now remember that the resonance are happening at two successive lengths of air columns. So this is the first mode of vibration, or any mode of vibration, nth mode of vibration, and this is the n+1 mode of vibration. So these are two successive lengths where we are getting the resonance, or two successive mode of vibration. That's why we should have what here, L2 minus L1 will give us here, as we know that L2 minus L1 will give us half a lambda. But we have the expression that we got already, 2L2 minus L1F. So directly we can calculate V equal to 2F L2 minus L1. So we have 2 times F, which is 460. Then L's are 0.558 minus 0.183, and this will give us 345 meters per second. So this is the end of our lesson. Thank you.